All right, so welcome. Today we're going to talk about density. And when I think of density, I think of how it's used as an insult, like, oh, that person's so dense, they're not very smart. And when I think of that, I think of poor Patrick Starr. So that's why that is the opening page of this slideshow, because Patrick's clearly not the brightest. He's nailing a board into his forehead. All right, so density, what is it? When we're talking about density, we're referring to how much matter is in an object per area. So it's not about total weight. The problem most people make is they compare density to weight, and although they're related, they're not the same thing. You can have something that weighs a lot that's not very dense, or you can have something that's really small that weighs a ton. It's all about it's how close the atoms are packed together. So if you look at this example, we have a scale. Now, if you're looking at the size of the object, these little cubes represent an area of space. Okay. And if you look at the amount of matter packed in tight in these cubes of space, you can see that this one on the right has way more matter in it, right? It has a lot more matter inside of it. Think of it like you are moving and you have got a cardboard box and you're packing stuff in it. This one is like pillows. You put 3 or 4 pillows in there. The box is the same size, but it's not very heavy. This one is like all the books you've ever collected go into this box. And even though this box is, like I said, the same size, it weighs a lot more because if you were to go and look at the size and the amount of the atoms in this box, all the matter that makes up inside of this box, this has a lot more matter than the other one. So it does weigh more, and it's also a lot more dense. All right, so pop quiz. Looking at these three objects, which has the most density? Which is the most dense? And hopefully, all of you pretty quickly gravitate towards this one right here. Even though this one's bigger, this one is going to be more dense because if you were to divide up this 10-pound weight into a bunch of little cubes, all the same size, and you were to take one of those cubes and compare it to the same size little cube over in this object versus, inside this beach ball, you would see, although you have the same amount of size, that there's a lot of atoms, there's a lot of matter packed really close in here. This one's kind of in the middle. It's in the middle between these two, and this one has very few atoms in that little space because inside this volleyball is just air. So there's not going to be nearly as many atoms. And even though this beach ball is bigger than this weight, it weighs a lot less. And most importantly for our discussion today, there's a lot less there's a lot less density, a lot less matter per area. Okay. So how is it measured? Like I said, it's matter per area, or more officially, grams. So that's a unit of weight, right? It's like pounds or tons, but we're measuring it in grams per centimeter cubed. So this cm cubed, I don't know if you've covered this in math yet, but we're just talking about this little area of space, this cube that we've been referring to. So if this is a centimeter and this is a centimeter and this is a centimeter, this little box we have, this little moving box like we talked about, is going to be 1 centimeter in all directions, just a 1 cubic centimeter. And how many grams are inside just this little centimeter is how we're going to measure our density. So this one on the left, let's say that just for fun, each of these green circles represents a gram of weight. Okay. So let's say 1, 2, 3, 4, 5, 6, 7, 8. If each of these little green circles represented a gram of weight, then this particular cube, or the density of this cube, would be 8 grams per centimeter cubed. And over here, if that's too deep, that is 9 times 2. That'd be 18 grams per centimeter cubed. So it would be 8 versus 8, or versus, 18 grams per centimeter cubed. And this one's going to have a lot more density, obviously, right? So that's how it's measured. Let's look at some real life materials that make up the earth, okay? These are we're going to cover 4 of the most common materials found in and on the earth, okay? So one of the most dense that we're going to refer to is nickel. Okay. So, nickel, we're not talking about the thing that's worth 5 cents. We're talking about the element nickel. And it has a density of 8.9 grams per centimeter cubed, right? 8.9. And that's what it would look like if you just had a block of pure nickel. So if you were to divide every 1 centimeter cubed area out of this, it would weigh 8.9 grams. All right, iron. So iron is also pretty dense, although it's 7.86 grams per centimeter cubed. So if you compare that to nickel, nickel's 8.9, iron is 7.8. So iron is still pretty dense, but it's a little bit less dense than nickel, just a little bit. Let's compare another one, aluminum. Now we have a big drop off. Okay. Now, when I think of aluminum, I'm sure you maybe feel the same way, but the first thing that goes to my brain is aluminum foil. That flimsy stuff you put over like the potatoes, the potato casserole in the fridge. We're talking about a solid block of aluminum, okay? Not just like the flimsy little foil. So, in a solid block of aluminum that's 1 centimeter cubed, you would have 2.7 grams worth of mass. Okay, that's how much material would be in a square centimeter of aluminum. Compared to iron and nickel, that's a lot less, right? Like 3 or 4 times less. And then finally, magnesium. So this again is one of the more common materials you can find that make up the Earth. These are like the building blocks of the construction of Earth. Now, are there thousands of other things that make up Earth? Yeah, like there's a lot of stuff that makes up the Earth, but these are four of the main ingredients, really. So magnesium, it's a measly 1.7 grams per centimeter cubed. Compared to the other ones, that is tiny, right? That's almost half of aluminum, even. So this is the least dense material of our little comparison here. So let's see why that is important in the construction of Earth. Before we do that, I want you to think about density, okay? Think about what that really means and ask yourself this question. If you were to put a bunch of tiny grains of nickel and iron and aluminum and magnesium in a jar like this and you shake it over a long period of time, what would you start to see happen? Visualize what I'm asking here. So, as this jar vibrates or as it's shaken, you're probably going to see things start to settle, right? The heavy stuff, or I should say the most dense stuff, is going to sink towards the bottom because there's more matter and gravity likes it more, right? Gravity's going to pull on it more. So as things shift around, you're going to see the more dense materials like nickel start to fall towards the bottom. You're going to have the iron fall just on top of that, and then the aluminum on top of that. And then here at the top, the least dense stuff, you're going to have um, all the magnesium. So again, imagine our cardboard moving box scenario. Imagine you put a bunch of stuff in that box. Let's say you put one really heavy weight, like that 10-pound iron dumbbell. And then let's say you put a pair of jeans, and then you also put a little fluffy piece of cotton, not on purpose, but let's say a fluffy piece of cotton that was got pulled out of a pillow or a teddy bear or something, accidentally kind of blew into the box and landed in there, and then that box settles. It bounces around in the moving truck for 6 hours. You're probably going to expect to see the heavy stuff on the bottom or the most dense stuff on the bottom, and the least dense stuff like the cotton floating around on top, right? And that's because things have adjusted according to their density, and that's what life does. That's how the world and the universe work. The most dense stuff is going to be pulled more by gravity and end up down here in the bottom, while the least dense stuff hangs out on top. So why is that important? Well, it created the world. So let's look at these different layers, and you've probably seen these before, but if you haven't, here's a refresher. The Earth is made of 4 layers. You got the inner core, outer core, mantle, and then this thin skin here on top. This is the crust. This is where we live, right here on the crust. So if you had to make a guess, what do you think these layers are made of? Well, it makes sense that if the rest of the universe organizes itself according to density, that the world would too, and it does. So The inner core, this is like the bottom of the box. Gravity pulls everything that's really dense towards the inner core. So, guess what the inner core is mostly made of? Yeah, you guessed it, nickel, the most dense material we talked about. Look back over your assignment if you're doing that right now. What is the next most dense after nickel? Yeah, it's going to be iron. So this outer core is made up of mostly iron. Now we get to the mantle. The mantle is made up of the next most dense material, the aluminum, and the crust is actually the least dense material that we find on Earth, and that's made of mostly magnesium. Now, if you're like looking around the ground, you go for a hike and you're like, wait a second, are you saying this is all magnesium? No, there's a good mix of a lot of stuff throughout here. But if you were to look at the inner core, you would find mostly nickel. And in the outer core, you would find mostly iron, and so on and so forth. There is a lot of magnesium on the surface of the earth. It's like the super common. And the reason that it's so common is because it is so um, non-dense. Or it has a small amount of density. This magnesium, if we go back to our moving box scenario one more time, this is like the piece of cotton that accidentally landed, um, in your moving box, and all the real heavy stuff has sifted to the bottom, and it's just like I'm content to float out here on top. The reason the crust is the crust is because it's made of less dense materials, and the reason the inner core is the inner core is because these are the most dense materials. Okay, I got one final question for you. What do you notice about how thick these layers are? So again, this chunk right here is the inner core. We've got a decent sized outer core. We've got a massive mantle right here. This is the thickest part of the earth. And then we have this tiny little crust. Really, this is comparable to like the skin of an apple. So think about biting into an apple, and the seeds are kind of the inner core, and then you got all that like white, fleshy, the fruit of the apple. And then you have like that dainty little skin on the outside. That's where we live, right here on the crust. And it's cold and it's rigid and it's made of all the solid rocks we see. And we're going to learn in our next activity exactly how deep these layers are. But I hope you realize just from this picture, they're made up of different densities and they have different thicknesses. All right. I hope that helped and good luck with your assignment.